So in today's agenda, we are going to look at all these things. What is big data? What is the hype about big data? And which is the reason for Hadoop? So before discussing Hadoop, we have to know what is big data and what are the limitations in the existing systems that led to Hadoop and why Hadoop basically. And then solving the problem with Hadoop. What problem does Hadoop solve? And why do we really need Hadoop? And then we have introduction to Hadoop. What is Hadoop? Hadoop ecosystem. What are the different things in a Hadoop system and core components? What are the main core components of a Hadoop ecosystem? And then we are going to touch MapReduce software framework to understand what actually is MapReduce, because Hadoop is based on MapReduce. So we're going to look at what actually it means by MapReduce whenever we talks about MapReduce. And then we are going to look at Hadoop Cluster Administrators, roles and responsibilities. What are the main things that a Hadoop Cluster Administrator does, and what are his main roles? And then we are also going to do an introduction to Hadoop 2.0, which is the latest Hadoop version being used nowadays. Right. So Apache Hadoop is a framework that allows for distribution frame processing of large data sets. So it's a batch processing system which allows you to run your big tasks in a distributed fashion. So if you have a huge data set, it will partition those data sets and run it in parallel distributed way across cluster of commodity computers using a simple programming model. So we'll again go through this in detail. It's an open source data management with scale out storage and distributed processing. So it's an open source system, and scale out storage means it scales well. You can keep on adding storage and still your results would be same, and it does distributed processing. So this is the logo for Hadoop. If you know, if you guys see elephant. So okay, so main key characteristics of Hadoop. What are the main characteristics that a Hadoop system should have? So let's start with reliable. So because Hadoop is going to handle your big data and it's going to be a production system, it has to be reliable. It cannot go down, or it cannot be like some days it gives results in 5 hours, next day it gives results in 10 hours, then again it goes to 8 hours. So it has to be reliable. Your nodes should be functional. They should be working all the time. You should be able to query data all the time. So that's the reliability aspect of Hadoop. And then it should be economical, that you don't have to spend millions and millions to every year just to get Hadoop working. It should be economical. You should be able to add nodes as and when every quarter based on your capacity planning. You should be able to add more nodes for your projected growth. And it should be scalable, that again, that if you have 100 nodes and you want to make it 200 nodes, it should not that you have to redesign everything and you have to take a 1 week of outage and you cannot do anything. So that's why Hadoop system should be scalable, because it's going to be used in production systems. And so Niladri says that these servers are designed to deal with huge data, but not extremely performance centric. So even though they have huge capacity, but they are cheap as a compared to performance oriented server hardware where we use SAN or SAS or SCSI drives. That's exactly correct. Yeah. So that's what we discussed, that these are uh, designed to deal with big data, but they're not very performance centric. They're not like server hardware, which is very high end and really expensive. And the next thing about Hadoop is flexible, which is the thing that we discussed a lot about connectivity, that Hadoop should not say that, okay, when I am in a company, no other tool would work. That's not the idea of Hadoop. Hadoop should coexist and should be very flexible. You should be able to talk to Hadoop from any kind of interface. If you have MySQL, you should be able to talk to Hadoop. If you have Flume, you should be able to talk to Hadoop. If you have Tableau, you should be able to talk to Hadoop. And if somebody does not know Java, he should be able to write things on Hadoop. So that's why Hadoop is very flexible in terms of connecting to different things and in terms of helping users to run things on Hadoop. You don't have to be Java expert to use Hadoop. You can just have basic knowledge about any shell scripting and you can still write code on Hadoop. So that's why Hadoop is very flexible. So, and question was Vikrant is that does Hadoop support virtual machine? Can we use VM instead of commodity hardware? That's correct, Vikrant. So VMware also actually came up with something last year, and they are still working on it, that they support Hadoop on their VMs. So you can definitely go and read about that on VMware website. Okay, so let's see a bit history about Hadoop. So it started as a project by Doug Cutting and Mike Caffarella in 2002, and in 2003, the big thing happened was Google published the Google file system and MapReduce papers, which are basically led to foundation of Hadoop. So initially, Doug Cutting was working on Nudge, which was another project, and then he added, which was basically a project at I think he was initially at some other company, then he joined Yahoo, and for basically indexing and looking at making sense of the user data. So he then added DFS and MapReduce support to Nudge in 2004, and then in 2006 Yahoo hired Doug Cutting, and then Hadoop became a full-fledged project. And then in 2007, New NY Times basically converted 4 terabytes of image archives on EC2 data, and then Facebook also launched Hive, which we will see is another tool on top of Hadoop, which is a SQL-based support for Hadoop. And then 2008, Yahoo basically published some numbers that they were able to do fast at 1 terabyte sort in 3.5 minutes on their 900 node cluster. And that's when Hadoop really started picking up. And then in 2008, Cloudera came into the picture, and then Hadoop Summit happened, and then Hadoop just since then Hadoop is just getting popular and popular, and then Cutting also went to Cloudera. So a lot of people, I think good people have went to Cloudera, so that's why Cloudera distribution has really improved a lot over time, and people really like using Cloudera distribution. And then there were like some more benchmarks, they keep on coming, and since then Hadoop has become like a mainstream, and every enterprise is now investing in Hadoop. This was a brief history about Hadoop, that how it started and where it is now. And now, as we just discussed, that instead apart from Cloudera, there are a lot of players in the industry who are basically working on Hadoop, and they are releasing their own distributions of Hadoop. So there's Hortonworks, there's Pivotal, there's MapR, and so that's why Hadoop is just getting popular. Okay, so I guess let's look at this website. That I guess everybody would be waiting for this. That what exactly are components in a Hadoop system? So, so as you can see, we have a Hadoop distributed system. So that is the core of Hadoop. So that's the file system. So Hadoop distributed file system is the file system of Hadoop, and all the data that you write to Hadoop gets stored in this file system. So it's different from a regular file system in certain aspects. So the main thing is because we are dealing with big data, so they so in these Hadoop distributed file system, we have big block sizes. So if you guys know that the data on a Linux system or any system is stored as a series of blocks. So if you have a file, it will be broken into certain number of blocks, and those blocks will be saved on your file system, and they will basically make a file. So that's the same thing with Hadoop. You will have a big file, it will be broken into a series of blocks, and those blocks are basically going to be stored on HDFS. So all the node, so somebody, I think Vinod or somebody asked that what are we going to know what is a node. So I think, yeah, now is the time to introduce node. So all the machines that we add to Hadoop system to make HDFS and do computation on Hadoop are called nodes. They are Hadoop nodes. So you might have, if you have say 10 node cluster, that means you have 10 nodes which are basically working as Hadoop distributed file system. So data is distributed across all of these 10 nodes. So when you write a file to Hadoop, you have say 10 GB file, and that file is broken into blocks, and so from 10 GB based on your block size. So by default, Hadoop block size is 64 MB. So, and a lot of most companies change it to 128 MB because increasing that gives better performance. So your 10 GB file would be broken into the blocks divided by this block size, and you might have say 15 blocks. And then Hadoop, there's a component called name node, which basically decides where it should store the data, and the data is basically stored on all the nodes. So that's what is Hadoop distributed file system. So Niladri has a question. One node is one server. So yes. So in terms of Physical server, yes, one node is one server. So if you have 10 servers that you are added, so those are 10 nodes, and your data will be distributed across all the nodes because it's a distributed file system. So that's the main, basically the fundamental of a distributed file system is you distribute data across multiple nodes so that the data basically is scattered and you can run them in parallel. If all the data goes on one node, then there's no purpose of having a distributed file system. So that's the main function. And then Hadoop distributed file system is different in terms of basically it has basically different in few things that we'll see in our further slides. That it has, first of all, the main difference, it has a bigger block size. The block size is 64 MB by default and 128 MB, and a lot of companies even change it to 256 MB. So that's the block size. And then another thing is that Hadoop is going to replicate the data and basically store data in multiple locations to avoid the failure. So Vinod Kumar is John, ultimately data stored in storage. So you can say storage, but then distributed file system is of course it is the storage that you are storing the data there. It's a backend for a lot of things, but then it also does some intelligent things that it will basically store 3 copies of the data. In case your one node goes down, you'll have 2 more copies, and it will basically move your computation to the data. That's the main important thing that we will see in Hadoop. So it's more than a storage, that it's an intelligent storage, an intelligent way of storing the data and then doing computations in a distributed way. So Raghunath is saying, is there a difference between hardware used for name node and data node? Yes. So that's also again something that we are going to discuss in our further slides. So name node and data nodes, I think once I introduce, so Raghunath, I'll keep your question for the slide when we go to name node and data nodes and explain it there. So remind me in case I forget, but I'll answer your question then. So name node basically has a different purpose than data node. Data node is something that as the name says, it stores the data. So it will have multiple drives storing the data. But name node is a node that will have bigger memory. It has more memory requirements than actual data requirements. So name node won't have a lot of storage, but name node will have more bigger memory than data nodes. And data nodes will have lot of storage and multiple cores. Name node does not need to have a lot of cores because name node is one process that takes care of the metadata of the system. But data nodes are the nodes we are going to store the data and they are going to run the computation. So they need to have a lot of storage, they need to have a lot of memory, and they need to have a lot of cores. So that's the main difference between the hardware. So hope that answers your question. So Vijay Kumar says, it is required that one node should be one server. Can we have each name node? Can we have each name node on each disk, say 4 disks on a server? Uh, I am not really clear about the second part of this. So can we have each name node on each disk, say 4 disks on a server? Okay, so basically, Vijay, we don't need those many name nodes in a Hadoop system, because what name node does is it just makes a note of where your data is residing, on which node, what block of a file is there. So name node just does that. So you don't really need multiple name nodes for every few disks. So you definitely need redundancy, that if one name node goes down, you should have something else. But you don't need, like, for every 4 disks, if there's one name node, then again you won't have the distribution across the entire network. So these 4 disks will be managed by one name node, next 4 by one. So when data request comes, you'll have to then find out which name node is going to handle that request. So that is again going to slow things down. So distribution of the data, basically we won't be able to achieve that parallel distribution and faster time. So Anurag has a question that, if I understand correctly, the name node contains all the indexes of the block stored on multiple nodes. Yes, that's what we just discussed, that name node is like the metadata storehouse. So it knows every block, it knows what are the blocks that a file is made up of. If a file has 10 blocks, it will have information about all the 10 blocks, and it will know where each of the 10 blocks is stored in the cluster. So one block could be on first node, second block could be on 10th node, third block could be on 5th node. So all this indexing is done by name node. So Vinod has another question. What type of storage we use, SAN or NAS? So SAN is storage area networks is another very expensive storage, and NAS network storage is again. So for Hadoop, we don't have to buy any expensive additional SAN kind of storage. We just buy regular machines which have hard drives. Mostly people go with SATA drives because they are more reliant in for fault tolerance, and they perform better. So you will just have drives attached to your node. You will have, say, different partitions. You might have, say, 5 partitions, and each partition is of 2 terabytes each. So you might have 10 terabytes capacity of a data node. So it will be just like a commodity node. You don't have to buy something like a SAN, which is very expensive. So I think SAN is like for 5 terabytes, you have to pay $5,000 or something. So SAN or NAS are very expensive. So we usually don't need that kind of things. And if you just pay 5,000 for 5 terabyte SAN, you might in 4,000 or 3,000, you might get just 10 terabytes data node. So that's why people go with this regular data nodes. When I say regular, it's like commodity, and they have high RAM, they have multiple cores, and they have multiple data partitions, and they each data node can handle 10 to, say, 20, 10 to ranging from 10 terabytes to about 30 terabytes of data. So any example of such storage? So Vinod, for that we just discussed previously. Let me quickly go back. That storage. So basically SATA. So if you see, all of them are SATA drives. So that's why most companies go with SATA, because it is more reliable and fault tolerant. Do we use SAN or NAS? So for Hadoop, no, we don't use SAN or NAS. So SAN is used by systems like SAS. So for Hadoop, we don't use SAN or NAS. So Vijay is saying for data node, no, we don't use SAN or SAS. SAN or NAS, sorry. So SATA delivers poor performance on random data, but offers huge data density, is what Niladri has to say. That's correct. So on random data, yeah, SATA might be slower, but for data density, where you have a lot of data on one drive, it is going to give you a better performance. So, and very good performance on sequential data. Yes, that's correct, Niladri. And Vinod Kumar is saying EMC released Isilian. Yeah, so EMC is also, I guess, partnering with Pivotal, and they basically, you buy Pivotal's distribution of Hadoop and you buy EMC hardware. So they say it works very better. So yeah, as you can, we'll see that there are a lot of companies who are basically working on different releases. So yes, that's true. And they say it's for big data. Yes, that's right. Okay, so let's go back to our core thing. So we just discussed Hadoop distributed file system, and on top of that, we have MapReduce framework. So basically, MapReduce framework is the framework where you actually do the computation. So HDFS is the storage layer, which is going to store the data, and MapReduce is the computation framework, which is going to basically run your jobs. And then we have MapReduce, and then we also have HBase. So MapReduce is for like sequential kind of data, and HDFS is for random reads and writes access. HBase, they are tables based on top of HDFS. And at the top layer that you see is Hive, Pig Latin, and Mahout. So these are the kind of basically systems that are built on top of Hadoop to basically use Hadoop. So Hive is a SQL engine, so where you can run SQL like queries, and it will basically at the backend submit a MapReduce job. Similarly, Pig Latin is another language for data analysis, where you give statements like insert into, store, dump. So you give that, and on the background it generates a MapReduce job. So these are the kind of languages which are created for people who are not very Java friendly. So they, and then for basically consistency and historical reasons, like there are a lot of analysts who have been using SQL forever, and they don't want to basically just go to Java and write MapReduce code. They still want to use their SQL skills. So for those kind of users, we have Hive, we have Pig Latin, and then we have Mahout, which is machine learning. So you can basically analyze your machine learning algorithms in this language on top of Hadoop. So these are the kind of tools that are available. And on top of that, there is Apache Oozie. So Oozie is a workflow scheduling engine where you can basically, like, it's like a cron job where you basically say that my jobs run my job workflow every hour or every day based on conditions. So we'll look at Oozie in detail later on also. So this is the Hadoop system. And if you see, we have to do import or export. Then we have a tool called Scoop, which is SQL on Hadoop. So basically, which lets you get data from structured data from Oracle or DB2 or those kind of databases to Hadoop, or it can get the results back from Hadoop to the databases. So that's the database connectivity that we have. So it's the connectivity tool for structured data, and for unstructured or semi-structured data, um, like do anybody would like to take a guess that what is a unstructured or semi-structured data? Anybody, any guesses on what would you consider as a unstructured or semi-structured data? Yeah, so Rudra says log files, that's correct. And Raghunath says video pictures, perfectly correct. Nandakumar says log files. Akash says sensor info, that's correct. And Vinod Kumar says data not stored in row and columns are unstructured. Yes, that's a good definition of data which is not in any format, which is like not a row format or column format. It's called unstructured data. You don't know if first record is like this, second record might not look like that. It might be something totally different. So that's an unstructured data. Clobs, yes, collections, Ravindranath says. And Vinod Kumar says like images. Yes, that's correct. Images are also unstructured. You'll have different format of every image. So they'll be in binary format, and each image will have a different binary format than the second one. So it would be an unstructured. And Vinod Kumar also says PDF. That's correct. And pictures. And Akash says log files. Vinod Kumar says audio. Suman Chandra says clickstream. That's correct. So clickstream means if somebody's basically on a website, they're trying to click something. So it has a stream. So based on what they clicked on, you might have different things in. So if somebody clicked on advertisement, it might have different properties. Somebody clicked on, say, a news link, it might have a different property. So clickstream is very unpredictable. It is unstructured. Yeah, so I guess everybody is perfectly fine, perfectly right. So these are the kind of data which are unstructured. So Flume is basically used to import or export data which is unstructured. So this is like a Hadoop 1.x ecosystem looks like. We have HDFS layer. On top of that, we have MapReduce framework to run the jobs. And on top of that, we have tools to basically shield MapReduce framework. You can just run SQL query. You can write Piglet in job, or you can do machine learning, and you don't have to really know MapReduce coding for that. And similarly, we have tools to get data on Hadoop. There's Scoop, there's Flume. So that is the Hadoop 1.x ecosystem. So any questions about this? So there's a question by Suman that Zookeeper is a scheduling tool, right? Where do we use that? So Zookeeper is not a scheduling tool, but Zookeeper is like a health check kind of tool which is basically used to find out the state, and it helps in deciding in like synchronizing the state. So we'll see that in 2.x. So Zookeeper is not a scheduling tool. For example, when you do name node HA, you will have Zookeepers, and they will help basically keeping the copies and syncing the data and deciding, and when some decision needs to be taken, they tell which name node has the latest information. So Zookeeper is like another things which are used for basically maintaining the state and in decision making. So again, this will something that we'll see in our further slides. So where do we use it? So Suman, as I just said, in name node HA you use Zookeeper, and in HBase also Zookeeper is used. So we'll see it as we proceed. Okay, so looks like some of this we already discussed that. What are the main core components? So we'll just quickly review it once more and add something more to it too. So Hadoop is a system for large-scale data processing, as we all discussed. So there are two main components. One is HDFS, which is Hadoop Distributed File System, which is the storage layer, which will basically be all the nodes in your system, and they are distributed. So whenever some data comes in, the name node will basically split the data in blocks, and it will decide which block needs to go to which node. So your data would be distributed across all these nodes. So when I say node, it means the machine which you have installed to act as a data node. And so when we say a node could be a data node, or it could be a task tracker, as we will see in amongst our future slides. So basically, when a node in Hadoop system basically does two things: it stores the data and it also runs the computation. So it's both data node as well as a task tracker. And HDF is natively redundant. So by default, HDFS, when it stores a block, it makes three copies of the blocks. So whenever a file is split into three nodes, so each of the node would be replicated three times in the cluster. So that is the how Hadoop is fault tolerant. Suppose you have three nodes and one node went down, you still have two copies of that block. So you don't have to wait for that node to come up and then do your job. You can still proceed with your job, and that's how redundancy is achieved in Hadoop. So we replicate the blocks, and each block is replicated three times. So that's the default replication factor. You can change it. Some people change it to two, some people change it to one also, but mostly I've seen people keeping it three. And as I said, name node keeps tracks of the location. So whenever any files come to the system, it will the request will go to name node, and name node will tell where what block is, and then you will access those blocks from those nodes. And then the second main component is MapReduce. So name HDFS is the storage layer, and the computation or processing layer is MapReduce. So what happens is, whenever something comes in, people are going to try to run jobs. So the data would be on HDFS. So suppose there's an input directory where you have two files and you are going to do some processing on this. So these two files basically are split into blocks, and then what would happen is there's a concept of job tracker basically. So job tracker is basically the job scheduling part of Hadoop. So the MapReduce, any job that comes, it goes to job tracker, and then job tracker basically schedules that job and gives the results. So like on HDFS, we have name node. So on MapReduce, we have job tracker. So these both name node as well as job tracker are called master nodes. And all the nodes, data nodes in HDFS layer and in MapReduce, it's called task trackers. So task trackers and data nodes are called slave nodes. And in most implementations of Hadoop, data nodes and task trackers, they both run on the same machine. That means if you have 10 nodes in the cluster and one node you configured a data node, you will also configure a task tracker on that machine. Similarly, on second node you configured a data node, you will configure a task tracker. So basically every node will have one instance of data node running and one instance of task tracker running. And and then so whenever a new job comes, so basically it comes to job tracker. So job tracker will basically find out, so if there were two files in the directory, so job tracker will basically find out the blocks that are basically for those input files. It will contact the name node, because name node is the only place where the locations of blocks is present. So name node is going to contact, so sorry, job tracker is going to contact name node, get the location of the data, and then it will try to near the data and assemble the results. What does that mean is, it will try to find out the data node where the data is, and it will try to run task tracker right there. So that is one very important concept in Hadoop that you all should pay attention to, that Hadoop brings computation to the data, right? So when I say computation to the data means, wherever the data is stored, it tries to run the job right there, so that it doesn't have to move data across, and that adds to the latency. So that's the main concept in Hadoop, that bringing the computation to the data. So that this is what job tracker does. Once it finds out the blocks that are the input data, it will try to see the block resides on this data node. So it will try to run the processing logic right there. It won't get the data from that node, move it to some other node, run the processing there, and then bring the data back to this node. So that's what happens with job tracker. And it nears the data, and then so if you have say 10 blocks, so each of those blocks basically will try to run the task tracker on that same node where the data is, and they will distributedly run the computation, and at the end the results would be combined, and then the results would be presented in the output directly to the user. So basically MapReduce makes use of the clustered storage, that the file has been split into multiple blocks. So it tries to basically run the computation or the logic for MapReduce on the node where the data is, and just gather results there. And then similarly, all these 10 nodes are doing this in parallel. So instead of running it like 10 times in sequentially, all these 10 run in parallel, so it's 10 times faster. And then at the end the results are combined, and then results are presented to the user. So 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 that's the role of job tracker, basically to split data into multiple tasks and try to run that task on each of the task trackers. So task trackers are the one basically way which are going to take, as the name suggests, they track the task. So they basically, so whenever a request comes from job tracker to run a task tracker will spawn a new Java instance, which is called a task attempt, and it's going to run that task and try to accomplish that task and sends the status back to job tracker. So if a job had 10 blocks, and so it will basically run 10, it has to run basically 10 mappers. So task tracker, so 10 task trackers might be running those 10 mappers, and they, once they are done, they will send their status back to job tracker, and then job tracker will basically compute all the results together, and the job will be finished. So those are the main two components, and in further slides, whatever we just discussed, we are going to see a graphical view of this. So there are some file system utilities and job scheduling and monitoring, web UI. So there is HDFS, there's MapReduce. In addition to that, there are some utilities to basically query the files. So you have to write the data to Hadoop, you have to read the data to Hadoop. So for that, there are some utilities. For job scheduling and monitoring, there are some tools that you can, once you submit a job to job tracker, so job tracker will start running the job on task trackers and get the results back. But if you want to see where your job is, there is a web UI for seeing that. So those are the additional tools that Hadoop provides. So whatever we just discussed here is presented in a picture format so that everybody can understand. So there's an HDFS cluster, and then there is a MapReduce engine. So HDFS cluster, you will have data nodes and name node. In MapReduce engine, you will just have job trackers and task trackers. So HDFS, which is the file system. So basically, whenever somebody talks about HDFS, then you should know that only things that are coming into picture is a name node and data nodes. There is no role of task trackers when you talk about accessing the data, because task trackers are supposed to run a task. When you try to read data from Hadoop, you're not running a task, you're just reading the data. So when you read the data, it goes to data nodes. And when you are trying to run the job, it runs on task trackers. So that's why we have split this as MapReduce engine and HDFS cluster. HDFS cluster is that whenever you try to save a file, it will go to name node, and name node will divide into blocks, and it will say that first data node will have first block, second data node will have second block, third will have third block, fourth will have fourth block, and it will make this entry in its metadata that this file is comprised of 4 blocks, and these 4 different blocks are living on these 4 different data nodes. And similarly, we have MapReduce engine. So in MapReduce engine, whenever somebody runs a job, that goes to MapReduce engine, that is a job tracker. So job tracker will then query name node. Suppose you want to run job and you say my input file is this, which is again on HDFS, and you want to run some processing logic on that. So job tracker will look at your input files, and it will then query name node that, okay, I have got this job that I have to run, and this is the input files. Can you tell me where the blocks for these files are? So name node will give it a list of the data nodes where the blocks are. So based on that, job tracker will try to just contact the task tracker and try to run task right where that data is. So it will basically split again based on the number of blocks in the file, and try to run these tasks on these task trackers in parallel. And task trackers will keep on sending their heartbeat back to job tracker that, okay, I'm still working on this. If it takes a long time, it will keep on sending a heartbeat back to job tracker that I'm working on this. And once all those tasks are done, then job tracker will basically send the status back to the user. So I think these are the main components. So I would ask everyone to basically look at this picture and think about what we just did and discussed in few slides, and ask me questions about this, because this is very important, that now that we are talking about the main core components in Hadoop, so it's very important that everybody understands what they are, and this is like the basis of Hadoop. So Ravindranath has a question that job tracker is executed on memory. Yes. So basically both name node as well as job tracker are memory intensive processes. So basically if you have a bigger uh, node cluster, you will always people will have more RAM and more heap allocated to name node and job tracker. And since they are going to track the all the task trackers, and you might, if you submit big jobs, you might have like 20,000 mappers in a job. So job tracker has to take care of that, all 20,000 mappers in that job. Plus you might have 20 people running such big jobs at the same time. So that's why name node and job tracker are very memory intensive processes. Yes, they use a lot of memory. So that's why in big clusters you will see that in all the big deployments there is a separate box for job tracker and a separate box for name node, because job tracker heap size can go high based on number of jobs that you are submitting. And similarly for name node, it has to maintain the metadata. If your cluster has, at some point of time, you might have millions of blocks in your cluster. If you have say 50 nodes, you have 100 nodes, you might reach to million of blocks. So name node has to keep track of all those blocks, which file is comprised of how many blocks, and where is each block residing on each which data nodes. So that metadata grows. So that's why in all the big deployments you will see that job tracker and name node are separate machines. And mostly I mean, it depends, but people gets like in bigger, if you have a 100 node cluster, you will see people have name node with say 50 gig RAM, job tracker with 50 gig RAM, though it doesn't go that high in memory. But usually if you have a cluster deployment, which is say more than 50, 60 nodes, it's always suggested to have a different node for a job tracker and a name node. And if you have smaller deployments, usually people have job tracker as well as name node on the same machine also. So Nanda Kumar has another question. Is it necessary to have all the task tracker or data nodes in a cluster to be of same hardware config, or is it ideal to have them of different hardware config? So definitely it's ideal to have the same config, but it does not always happen, because when you are talking about say 1,000 node cluster, and you keep on adding machines every time, every few months hardware configuration changes and new machines come up which are better in memory, which are better in cores, better in hard disk. So you cannot always have similar hardware. So in most big deployments of Hadoop, when I say big, like you say like 200 node cluster, 500 node cluster, 1,000 node cluster, or more than that, you cannot have same hardware. So it won't be same, so it varies. But for smaller deployments, somebody is starting with a 50 or 100 node cluster, they will definitely try to get similar hardware. So it's not necessary, but it's advisable, but it doesn't happen. So for example, if you have 6 2 terabyte drives, and nowadays everybody is going towards 4 terabytes drive, so you might, if you had your built your cluster 2 years ago and now you are building your cluster, so 2 terabytes drive will be there, and you'll have 4 terabytes, so there'll be a mismatch of hardware. So Hadoop allows that, and I think there were some issues with that Cloudera has fixed now. So you can now have mismatched hardware. So what used to happen was like 2 terabyte drives used to fill earlier than 4 terabyte drives. So there was some issue that actually in Cloudera latest release 4.5 they have fixed that. And even data movement across all the drives on a node. So as we said that each data node will have multiple drives, so you might have 6 to 8 drives. So between those 8 drives also, sometimes some drives used to get full before other drives because name node was giving the data, but it was sending in round robin fashion. But there was some defect that some drives used to fill earlier than other. So that was another side effect that Cloudera has fixed recently in 4.5. So that's something that does not happen. So people have mixed kind of hardware. So another question by Akash is, can there be more than one job tracker and admin node in a cluster? Yes. So that's also something recent that has been added. So as you might have heard, if you haven't, if you know a little bit about Hadoop, you might have heard that everybody used to say name node is a single point of failure. We cannot use Hadoop because if name node is down, everything will be down, which is true. If name node is down, then basically you cannot access data. Nobody knows where data is because name node is the only place where you know this file is this blocks. So name node is the only place that knows. So it used to be a single point of failure, but as Hadoop has evolved, so all the people have contributed in Hortonworks. I think mainly has worked on adding HA, high availability to name node, as well as job tracker. So now we have HA available, and it's used, I think, in most of the enterprises are using HA. So can you have more than one job tracker? You can have more than one job tracker, and you can have name node job tracker high availability. So you can configure 2 name nodes. If one job tracker goes down, then the second one will come up right away, and your jobs will be picked up from right where the previous job tracker left. So your jobs won't fail. But previously, if job tracker used to fail, everything in the cluster, all the jobs basically in the cluster will fail. The cluster won't fail because HDFS is still up. So till the time name node is up, you can query the data. But if say name node is up and job tracker goes down, so you cannot run the jobs, but you can still query the data. But if name node is down, then you cannot do anything, because even if you submit the job tracker still needs to contact name node to find the location of data. So that's why now we have name node HA, and I think that helps with the issue of name node being single point of failure. And Niladi says, I think that is the beauty of Hadoop, to accommodate diverse capacity hardware in a distributed cluster. Yes, Niladi, that's true. So even when, so if you have like a smaller node of, like small cluster, you had like 50 to 70 node cluster, and then you had a variable like diverse hardware, then it used to create some problems. But if you say have a 500 to 1000 node cluster, so in that case you don't need to worry about different kind of hardwares because you have to configure them that way. So yes, so Hadoop is able to handle that. So Suman has a question: how the search performance is managed in name node when we have millions of blocks? How the search performance is managed in name node when we have millions of blocks? So Suman, as we discussed, so name node basically creates this metadata of every file. It will basically try to have a metadata of every file comprising of how many blocks. So whenever somebody requests, so whenever you are making a request to Hadoop, you're always going to do it on a file basis, that I want to read this file, I want to read this directory. So as we know that um, a directory is made up of files. In Windows or Linux, everywhere a directory has a list of files in it. And so name node will basically, when you try to read a directory, or you try to basically read a file, then you will send that request to name node. So name node is going to basically just look at that file in this in memory. It will be in memory, so it will look at that file and find out the blocks, and it will give those list of those blocks back to the user, basically the client, and then they are going to read the data directly from data nodes. So that's how basically name node handles that. And So next question is, so if hardware configs, so that's a question by Nanda Kumar. If hardware configurations are different, the task divided might take uneven times to finish. I believe that would be taken care by job tracker about waiting for the node to complete its designated task. Yeah. So when your hardware configuration are different, then you will basically say, so as we proceed, we'll see that each task tracker, you will define certain number of mappers and reducers. So there's a maximum limit that on every task tracker you can run 5 task trackers, you can run 5 mappers, you can run 3 reducers. So based on your different kind of hardware, you will define these kind of limitations on your machines. So a machine that has 10 cores, you will say maybe 7 mappers, 3 reducers. A machine that has 6 cores, you will say 4 mappers, 2 reducers. So based on that, when job tracker tries to contact the task tracker with 6 cores, and if 4 cores are available, it will run only 4 there. It cannot run more than 4. Then it will go to next task tracker and it will see it has 10 cores, so it will try to run rest of the cores there. So that is something that is taken care by Hadoop, and which is the main distributed architecture of Hadoop, that the computation would be taken care of by the job tracker to be evenly distributed, and all the task tracker that are available and then take the load. So job tracker will just choose that task tracker. So it tries to run the task tracker closest to the data, but if that task tracker cannot run for some reason, then it has to choose a task tracker and move the data to that task tracker. Hope that answers your question. So Vinod wants to say, do you give 5 minutes break? Yes, Vinod. Actually, my plan is to, after this slide, after answering all the questions about this slide, I want to give a little break for everyone for tea. Okay, yeah, Vinod. Yes, definitely. It's a heavy dose, right? So you need some tea. So Vinod has another question. Can we configure cluster in blade center blades? Can we configure cluster in blade center blades? I could not really understand that. So when you talk about blades, you are saying is like machines which don't have a lot of disk drive, right? So there's a concept of blades and bricks. I think you might be talking about the same thing. Blade center consists of 10 to 14 blades. So as far as I know, blades are like machines which don't have a lot of data capacity. So that the bricks are the machines where you have data of capacity. So you can use blades to maybe run name node or job tracker, but I think for the actual nodes you will have to use bricks. Okay, so there's another question by Gandhi Papineni, that once job tracker submits a task to specific node and for some reason if data node is down when half the task is done, does session continues where it was left on the failed node, or task will be resubmitted to a different node and has to start from scratch? Yes, that's a very good question. So the question is that suppose job tracker submit task to a specific node on a task tracker, and for some reason that node went down. So you said data node, but it would be just the node went down. So in that case, yes, that so what would happen is when the tasks are submitted, they send periodic heartbeats to job tracker. If a task takes say 10 minutes, so every few minutes it is going to send a heartbeat to job tracker that I am alive. So basically heartbeat means that I'm alive. So if job tracker doesn't get that heartbeat, then it knows that that task has died and it will reschedule that task on another node. And does that session continue from where it was left on the failed node, or task will be resubmitted to a different node? Yes, so task will be resubmitted, because if you try to save the state and try to move the data to different tasks in the, you might as well just start it again, because there's a lot of network movement involved, and it introduces latency. So usually you will see that whenever job tracker submits a task, it always runs 3 task attempts. So basically a task has something called task attempts. So whenever a task is started, 3 simultaneous tasks are started. So which of whenever first one finishes, rest 2 are basically killed. So that's also a configuration that we'll see. So most job trackers run with this kind of configuration, that you start a task and you start 3 attempts of that task, so that in case one of them fails, then automatically rest 2 are running. Job tracker doesn't have to do this once the job fails. So job tracker is smart enough to take care of this at the start of the job also. So hope that answers your question, Gandhi. Next question from Raghunath is, do we need to modify the name node hardware as we scale out the data nodes? So that's why I said that in a bigger deployment, it's always good to start with a higher end memory configuration for name node, because name node and job tracker are memory intensive nodes. They don't need any data storage on them, but they need a lot of memory. So if you see any big deployment, when I say big deployment, maybe more than 100 nodes, you will see that people start with 10 to 20 gigs of heap size for name node. So yes, for a big cluster, if you if you know that your cluster is going from 100 to 500 or from 500 to 1000 in next few months, is always good to have nice hardware for name node, because as you know, the hardware changes every few months. Every few months a new kind of hardware comes up which is better. So it's always good to start with the latest hardware which has better memory capacity in terms of running name node as well as a job tracker. Okay, so Vinod Kumar said about Blade Center, and Nanda Kumar said that yes, it's possible. So if it has 10 to 14 blades, so I'm not clear about what blades are, but talking about the blade servers in a rack. Yeah, so okay, so if there are servers in a rack, yes. Okay. So blades are low form factor servers fit into blade chassis, and they are identical to rack servers, have low DC footprint. Okay. Yeah. So I think, yeah, in that case, it should work. So in this slide, we're discussing about name node and data nodes. So as we saw that name nodes and data nodes, they comprise Hadoop distributed file system, HDFS engine, which a lot of time people call HDFS engine. So basically it contains name node, which is the master of the system, and which maintains and manages all the blocks that are present on the data node. So as we discussed that, basically name node is the metadata house of the system. So anytime any request comes for looking at a file on a system, it goes to name node, and name node tells that this file is made up of 6 blocks, and these 6 blocks are on these nodes. So then the client basically this goes back to those data nodes, fetches the information directly from those nodes. So name node basically does the act as the master of the system, as you can see by this fancy car that name node is the master, and data nodes are like regular cars. So they are basically like slaves which are just standing there to serve, and they are storing the data, and they are basically, whenever some request comes to read the data or write the data, they basically just serve that request. So name node is the one who decides that where the data would go, and then the data just goes on those data nodes. So they are basically slaves, and they run on every machine in the cluster, and they provide the actual storage. So that's why data nodes, we discussed that data nodes have usually are like 5 to 7 drives of certain terabytes each, base which ranges from 2 to 4 terabytes. So most systems you will see that data nodes are having like 6 to 8 different drives, and each ranging from 2 terabytes to 4 terabytes, and they are responsible for serving read and write requests for the clients. So that's, we just discussed that whenever client wants to read something, they go to name node and they get the blocks, and then those requests can come to actual data nodes, and then data nodes send the data back to the clients. And similarly, when somebody wants to write something, they go to name node. Name node sees the status of the system, that which data node has less data, it decides to move blocks to that system so as to try to basically balance the system. So that's how name node and data nodes, they work together for the basically the HDFS component of the system. John, do you have any real pics of the cluster? So when you say real pics, means like pics of the racks. No, I don't have any real pics of the racks and the nodes there, but you can imagine that mostly they are like big racks, and you might have say 12 to 20 nodes in one rack, and then you have another rack which has another nodes. So So basically, at most data centers will look like racks, and those racks will have the actual nodes, and some of the nodes will, and name node and job tracker might be part of it. There might be some different configuration of the node. So that's how cluster would look like. Yeah. So real picture, I'm not sure. Maybe you can ask in learning management system if they somebody clicked a picture of a real data center. But you can visualize it like they are like big racks, and and there are slots for different machines. So each rack will have, say, 15 to 20 machines. Second rack will have another 20 machines, and these two racks combinedly form the cluster. So Niladri says she can help. Yeah, Niladri, that would be great. So So Niladri is asking for email address for Vinod. So I'm not sure how that works. So maybe Niladri, you can maybe Vinod can open some help desk ticket, I guess, and then Niladri can respond. I'm not sure how that works. Yeah. Okay. So Vinod has given his email. So maybe after this session, I guess we can talk about that. So this was basically about name node and data nodes. So let's go to the next slide, which is again something that we briefly touched. So there's also a secondary name node. That's something that we haven't discussed as of now, but then as we said, that name node is like the main metastore house. So all the metadata is housed in name node. So if in case name node goes down, then you have nothing in your cluster. So basically nothing will work on your cluster. So that's why there's a concept of secondary name node here, which is not as it sounds. It's not a secondary name node per se, that it's not that whenever name node goes down, this node will come up. It is like a checkpointing node, which will checkpoint the name node data every hour and make a copy of the data every hour and just backs this up. So in case name node goes down, you can get the backup from the secondary name node, and just use that metadata backup to basically bring the cluster up. So that's why lot of one dot Hadoop 1.x deployments where you don't have name node HA, you will see everybody runs a Hadoop a secondary name node basically, so that in case name node goes down for some any reason, it could be hardware failure, it could be out of memory or anything. In that case, if you don't have any copy of metadata, then basically you don't have anything on your system. So that's why it's very important to um, make a copy. So that's a question by Vinod also. So if a name node goes down, what happens to production? Yes. So if the name node goes down, basically your cluster is down. You cannot submit requests to read data, write data. You cannot submit any jobs because everything goes through name node. So that's why name node is in all. That's why I guess name node HA is implemented, because otherwise name node is considered a single point of failure, and people were not very um, you know um, comfortable installing Hadoop in their production systems. But that's why Hortonworks and Cloudera have worked on HA solutions, and now we have name node HA, and that takes care of this problem. But that is Hadoop 2.x deployments. But in Hadoop 1.x, it's still name node and then a secondary name node. Plus, it's also suggested that apart from secondary name nodes, it can happen that both name node and secondary name node go down at the same time. So when you write metadata, it's always good to have like a network filer where you can also write the metadata. So name node writes the metadata in its local directories, but you can configure it to write to a network location also. So that way you will have a copy of network filer. So that's how most people do that. They try to make multiple copies of the name data, one on secondary name node, and then name node also it will write on multiple drives on name node, and then they will also try to write on a network filer. So that's how most people take care of name node. So hope that answers your question. So where will that backup be stored? So that's, I just answered that question, Nasima, that the backups. So if you have multiple drives on name node, people try to configure name node to write to both of those directories, so that if say one drive goes fine, then goes bad, then second drive can basically have the copy. So name node will still be up, and then there is secondary name node and then if secondary named also goes down, then the other thing is a network filer. And hopefully network filer won't go down because if that goes down, then we don't have anything. As per slide, a question by Vinod, secondary name node we can help build but not failover. Yes. So secondary name node is not a failover kind of node. It is named secondary name node, but that's a misleading name. It is just a checkpointing node, which basically every hour goes to name node, gets the copy of metadata and stores it on its own system. So Raghunath has a question, are number of writes less compared to read in Hadoop? Yes, so I guess so that's system is that you basically want to run your computations. Once you get the data on Hadoop, you want to do is read the data and run the computations. Yes, so number of it varies. So basically you will also write the data to Hadoop. You will upload data every day on Hadoop to basically run computation. But most of it would be like reading the data from data nodes and doing something on it and generating the final results. So yes, reads would comparatively more on a system where people are trying to run jobs, because everybody would try to do something on the data. If Google stores some data, then there might be analysts in Google, there might be engineers in Google, there must be some directors at Google who want to run jobs on that same kind of data. So everybody's trying to read that data at the same time. But when we wrote the data, we just wrote it once. So yes, definitely reading is more. So how do you achieve HA name node? Is a question by Niladri, by using a hardware cluster. So in HA, so that's something that we'll also discuss. So for HA, we use a quorum-based solution where we use zookeepers. So that's something that we'll also discuss in our further slides. So basically, we configure name node, multiple name nodes, and all of them basically have a quorum storage where they will write the data, and then zookeepers would be there to identify which name node is up and has the latest copy. And if say one name node goes down, zookeeper will identify the other name node which is up and make it the primary name node. So we will see that in our future slides. So by using a hardware cluster, yes, we have to add an additional node which would be the real secondary name node. So Raghunath has a copy. Does Hadoop maintain read consistency in case of data being written to the HDFS? So read consistency. So suppose somebody is trying to run a job on a data written on HDFS. So you're saying is, would Hadoop maintain read consistency? So when people run job on Hadoop, so if you have it's like all or none. So you have either all the data or you don't have any type. Somebody, if you are running a job and in between somebody deleted that input directory, so the data would not be there and the job would fail. So in that case, you'll have to basically rerun the job. And even if you have written suppose you had like 20 tasks and 10 tasks had already written their data, but 10 was still running, and then somebody deleted the input data and they rewrote the data. So in that case, the jobs will fail, and the intermediate data of those 10 tasks would also be deleted by name node, and there would be no output, and you have to rerun that job. Okay. So Niladri got answer to her question. So Vinod Kumar is, if we have 100 terabytes and have 50 nodes, how can data be stored means divided into nodes? Yes. So basically you have 50 nodes, right? So it depends on what is the storage on your node. So if you say each node has 6 drives of 2 terabytes each, so that means each node can have 6 into 2 times data, which is 12 terabytes. So and you have 50 nodes, so that means 12 into 50, you can store 600 terabytes. So that means every node will have some part of the data, and this 100 terabyte data would be split across the nodes. So I hope that answers your question, Vinod. Do I have to add storage onto nodes? No, so again, it depends on the configuration of your nodes. So if your node, each node can handle few terabytes of data, say each node can handle 6 terabytes of data, then 50 node would make 50 into 6, 300 terabytes of data, and your data is 100 terabytes. So it would be handled by this cluster. But if you take replication into picture, so when you say 100 terabytes, if you have 3 replication, then Hadoop is going to make 3 copies. That means Hadoop needs 300 terabytes to store 100 terabytes of data. So in that case, if you have 50 nodes, each node has 6 terabytes, so 50 into 6 would become 300 terabytes. So that means you have 300 terabytes of nodes and 300 terabytes of data. In that case, you will need to add more data. So basically, sorry, you have to add more nodes, because if you just store everything on the nodes, then when you run computations, you cannot do anything. There's no space to store intermediate data. So that's why whenever you plan for a Hadoop cluster, you have to do a proper capacity planning to make sure that you can add your data, and you, even after your data is added, you still have 30 to 40% storage space available to run the jobs, because when jobs run, they are going to generate some intermediate data that is going to be written on data nodes also. So if everything is just data and there is no space to run anything, there's no space to store intermediate data, then your jobs won't run. So that's why you have to do a capacity planning. So that's why every big company does every quarterly capacity planning, and they look at what data is coming every day, what new data is coming, and based on that they look at how much storage they have, and they keep adding new nodes to the cluster. So that's something that you will also have to do as part of your Hadoop administrator job.